we have seen in the previous class about the rotating magnetic field produced by the induction motor, and right, and the equations of the flux produced by the three-phase currents of the stator. Uh, and the outset we have seen about how the induction motor works, or the working principle of the induction motor, right? So the important here is that you must remember that the rotating magnetic field will have uh, a magnitude equal to how much? What is the magnitude of rotating magnetic field?
1.5 times
1.5 times pi max. Okay, so pi max is the maximum value of flux produced by any phase, any three phases, any of the three phases. So that is a magnitude, and related to sorry, its speed. What about the speed of the rotating magnetic field? Hmm? What's the speed of the rotating magnetic field? Or will it is a stationary flux, or it is a rotating flux?
rotating.
It is rotating, right? So its name itself is rotating magnetic field, right? So because it is rotating, means it is having some speed, right? So did we talk anything about the speed of the rotating magnetic field in the yesterday's class?
No, sir.
No. Okay, so then let us talk about it in today's class. So today's date is 24th, right? So 24/06/2021. So this magnetic field uh, or the magnetic field or the resulting magnetic field of the stator is rotating in nature, right? So rotating magnetic field, it is nothing but it is similar to a magnet rotating. A permanent magnet, if you rotate with certain constant speed, then its field also rotates with the magnet, right? So it is like that only. So rotating magnetic field. So its magnitude phi suffix r is equal to 1.5 times phi maximum. So phi maximum is a maximum flux due to any phase. Okay. Now its speed of the rotating magnetic field is equal to ns 120 into frequency divided by poles. Okay, so ns is equal to 120 f by p. Okay, so where f is a frequency of supply or power supply. Okay, so and p is a number of poles, sorry, number of poles for which P is equal to number of poles for which the stator winding is done. Okay, so that is the speed of, so the speed is given by this formula. Okay, so ns is also called synchronous speed. So it is the speed of what? Is the speed of rotating magnetic field. Okay, right? Three fluxes are produced by three windings of the stator, right? So those three fluxes they are phasors. So resultant phasor or resultant flux of these three rotates at a speed called synchronous speed and is given by 120 f by p. So it is denoted by n suffix s. Okay, it is called synchronous speed. So this is very, very important, right? Most importantly, it is the speed of rotating magnetic field. Okay, it is not the speed of motor. It is not the speed of the motor, right? Inside the motor you are having stator. So the stator is a three-phase distributed winding. That means three windings will be there. Those three windings are fed by a three-phase supply. So those three windings produce a three fluxes. So resultant of these three fluxes is called rotating magnetic field, right? So that clarity you must have. Okay, so that you should not miss, right? So but then what is the speed of motor then what about speed of motor speed means the rotor, how at what speed it rotates, or the shaft at what speed the shaft of the induction motor rotates. Okay, so in the previous class I told you that you are having a, a stator. So instead of the stator, so so instead of the stator you are having another winding, right? So if we keep winding inside, so you will have so three windings. So all are 120 degrees uh, displaced in phase, right? So this is winding one, winding two, winding three. Okay, so this these three windings will produce three fluxes. So the resultant flux produced by these three is it rotates at a speed of ns. So ns, right? So this ns, because of this ns, the rotor which is inside of it is also having conductors inside of it. rotating magnetic field. So it rotates, and because it is rotating, the flux linking the conductors of rotor will change, right? So the flux linking the conductors of rotor will change. So as a result, you will have induced EMF. Okay, so that induced EMF, uh, that induced EMF causes some current to flow in the rotor. When these currents, so rotor conductors. Okay. So because the rotor conductors are stationary, right? The flux linking these conductors is changing. You will have induced EMF. So that induced EMF causes some current to flow through the rotor. So and hence the rotor is carrying current and is in the magnetic field. It also starts rotating, right? So why does the EMF induces in the rotor conductors? Why does EMF induces in rotor conductors? It is because of relative speed between rotating magnetic field and rotor conductors. Okay, if the relative magnetic speed between these two is becomes zero, right? If the relative speed between rotated magnetic field and rotor conductors becomes zero, there will be no change in flux linking the conductors. Flux linking will be there, but there will be no change, and hence there will be no induced EMF. Okay, so that is the important thing, right? So the EMF induced in the conductors depends upon the relative speed. If the relative speed is more between, right, the relative speed between this field, stator field, and the rotor conductors is more, then you will have more induced EMF. Okay, so here important thing is the relation between rotor speed and the stator field speed of the rotor and the field speed, right? So here the slip, one term called slip is important. Slip, so it is a difference between speed of RMF and rotor speed. Okay, so percentage slip is equal to S is equal to NS minus N divided by NS into 100. Okay, relative speed NS minus N is, sorry, so N is a rotor speed or speed of the rotor, and NS minus N is called slip speed. So S is slip and that is given by NS minus N by NS. Okay, so this is very important. That means if there is no relative speed between a rotating magnetic field and the rotor conductors, there is no induced EMF. So if there is no induced EMF there, in the rotor, there will be no current in the rotor windings or rotor conductors. So if there is no current in the rotor conductors, there will be no force acting on the conductors, right? So if there is no force acting on the conductors, the rotor will not rotate. Is it clear? Hello.
Yes, sir.
So slip is very important, right? Now from this, S is equal to ns minus n by ns. So n it becomes how much? S into ns n is how much?
120 F by P, sir.
ns minus sns. Okay, from this equation, so n is equal to ns into 1 minus s. Okay, so rotor speed equal to 1 minus s times rotating speed of the rotating magnetic field. Okay, now frequency of a rotor current. How much frequency? Speed and frequency are always related in AC motors. Okay, speed and frequency are always related. Okay, so rotor current frequency, say F in this formula, this F is a what is the F we gave here? F is a frequency of the power supply. Okay, frequency of power supply, right? But here what we are talking about is a frequency of rotor EMF or current, because in the rotor the EMF or current are induced by the stator, right? So at what frequency these are induced in the rotor? It depends upon the speed between the rotating magnetic field and the rotor, right? So say at any speed, that means if the relative speed is more, its a frequency will be more. Okay, so here ns relative speed is given by ns minus n is equal to 120 f dash by p, where f dash is equal to rotor current frequency, right? So here, and ns, what is ns? Ns is equal to 120 f by p. What is this ns? Speed of the rotating magnetic field. And what is n? Speed of the rotor. So the difference between these two speeds decides the frequency. So that's why. So to obtain relation between f and f dash, right, we can divide. Otherwise, from this one, say from this is equation 1, 2, from 1, f dash is equal to ns minus n by p
NS,
120, right? And from 2, f is equal to ns into p by 120. Okay, So this is 3 and this is 4. 3 divided by 4 gives f dash by f is equal to ns minus n into p by 120 into 120 by ns into p. So p gets cancelled, 120, 120. Okay. So f dash by f is equal to ns minus n by ns. So that is nothing but slip. So f dash is equal to s into f. So this is the relation we can obtain between the stator frequency and the rotor frequency. Okay. So rotor current frequency. Therefore, rotor current frequency is equal to slip multiplied by stator frequency, or the supply which is given to the stator. It's a frequency, right? That supplies frequency. Okay. Is it clear? So in this, is there any doubt? If you have any doubt uh, up to this point, what I have taught in today's class, quickly ask your doubts if you have one. Okay, then if there is no doubt, we can go to the next topic. Let us do a simple problem on this slip and frequency of rotor. So note down a problem. A slip ring induction motor runs at 290 RPM at full load, comma, when connected to 50 Hz supply. Determine the number of poles if synchronous speed or is 300 RPM. Okay, so rotor speed or n, not n, some textbooks they will rotor they keep a suffix r as a suffix to represent that it is the speed of the rotor. N is equal to 290 RPM. The frequency f is equal to 50 Hz. The synchronous speed of a speed of rotating magnetic field ns is equal to 300 RPM. So do you think that we can calculate speed number of poles? Hmm? So we have ns is equal to 120 f by p. So that is 300 is equal to 120 into 50 by p. That implies p is equal to how much? 3 4 20. Okay. Number of poles is equal to 20. Okay. Now slip also you can calculate. Also calculate slip. Slip is equal to ns minus n by ns. That is 300 minus rotor speed 290 divided by 300. So that is 10 by 300. 1 by 30. 1 by 30 is how much? 10%? 1%.
0.033.
0.03. So 0.03. So percentage slip is equal to 0.033. Percentage slip is equal to how much? 3.3%. Okay. Is it clear?
Yes, sir.
Sir, once you can see, show the above slide, sir.
This one?
Yes, sir, that one.
Hmm. Over?
Done, sir.
Okay, next problem. A 4-pole 3-phase induction motor operates from a supply whose frequency is 50 Hz. Calculate one speed, the speed at which the magnetic field, the RMF rotates. Second one, the speed of the rotor. The speed of the rotor when the slip is 0.04. Third one, the frequency of the rotor currents. Sorry, it has gone. the frequency of the rotor currents when the slip is 0.03. The fourth one, the frequency of the rotor currents at standstill. And standstill condition, what is the frequency of the rotor? What is the data given here? Number of poles for supply frequency. F is equal to 50 hertz. Okay. So first one is a speed of the RMF. It is denoted by n suffix s. That is synchronous speed, right? So what is the speed of this? Ns is given by 120 f by p. That is 120 into 50 by 4. Okay. It is 1500 RPM, right? So second one, the speed of the rotor when the slip is 0.04%. N when s is equal to 0.04. Okay. So n is equal to what? Ns into 1 minus s, right? That is 1500 into 1 minus 0.04. So this is 1500 into 1 minus 0.04. How much it is? 1440 RPM. Third one, the frequency of the rotor currents when the slip is 0.03. So frequency of rotor current when slip is equal to 0.03, right? So we have relation f dash is equal to s into f, right? So rotor current frequency f dash is equal to 0.03 into 50. So it is 1.5 hertz. Okay. Fourth one, frequency of the rotor currents at standstill condition. F dash at standstill condition of rotor is good. How much? First of all, what is standstill condition? What is the standstill condition? It is this. It is the instant. What is standstill? Instant at which the supply to stator is switched on. So it is the instant at which the supply to stator is switched on, right? So before the supply is given to the motor, how much is the speed of the motor?
0, sir.
0, right? Before supply is switched on, speed of motor is equal to 0. At the instant, so at the very instant supply is switched on, speed is also speed is 0, right? That is n is equal to 0. So the question is what? F dash at standstill condition. So at n is equal to 0, f dash is how much? Okay, so f dash is equal to s into f, right? But s is equal to ns minus n by ns. So that is s is equal to ns minus 0 by ns, that is 1. So therefore f dash is equal to 1 into f, that is f. That means at the instant the switch of the power supply is turned closed, the motor rotates. It is not rotating, so it is 0. So at that instant, the EMF induced in the rotor will have the same frequency as that of the power supply. That means at standstill condition, induction motor is nothing but a transformer. Transformer will have both on both primary and secondary, or on high voltage side and on L voltage side, it will have same frequency. On both sides, it is having the same speed, no speed in the transformer, right?
Yes, sir.
Okay, is it clear?
Yes, sir.
So f dash is equal to f at a standstill condition. So f dash is equal to 50 hertz. Now, after this instant, when we switched on the supply, the rotor starts rotating. Okay, slowly it picks up the speed because of the relative speed between rotating magnetic field and the rotor conductors. There will be induced EMF, and it causes some current to flow through the armature, rotor conductors. So as a result, a torque is developed and the rotor starts rotating. Okay, so slowly it picks up the speed, right? As it picks up the speed, what happens? The relative speed
Decreases.
decreases, right? Okay. After power supply is switched on to the motor, right? The current induced in rotor causes some torque. So the rotor starts rotating. Therefore, ns is no more equal to, n is no more equal to 0. Therefore, slip is not equal to 1. Okay. So, and it is not equal to 1, but slip less than 1. Okay. Therefore, f dash is equal to sf. So f dash will be less than f. Okay. So f dash will be less than f under rotating condition. As long as the rotor is rotating, the frequency of the rotor supply will never be equal to supply frequency. Okay. So that means the slip plays an important role in the operation of the induction motor, right? So after power supply is switched on to the motor, the current induced in rotor causes some torque, so the rotor starts rotating. Okay. So with increase in speed, slip decreases, but rotor frequency decreases. Okay. And rotor frequency also decreases. So this is a what the slip, the synchronous speed, rotor speed, frequency of the rotor induced current, and EMF is. Okay. So today's class we have solved two problems, and we have seen what is the slip and the related things. Right. If you have any doubt, you can ask. Else, we can. Otherwise, I will end the session. Mokshit.